So as Chris said, this talk's been postponed twice. Once was on my half of being sick, and on the other part was I'll have to blame that one on Chris. But I'm glad that you turned up today, so thank you very much. I was worried there was either going to be nobody coming, not believing I'd turn up again, or there'd be much anticipation, so I'm glad that there's a few people here. So as Chris said, I'm going to talk today, give you some case studies of how our tsunami science at GA has been influencing decision making on disaster risk reduction in the region. And I'm going to be talking a little bit about our AusAid funded project. So when I first came, I started doing some domestic hazard work, and then since then I've been working in the region. So those are the case studies that I'll be talking about today. But I'd like to start by telling a tale about two tsunamis. Now these tsunamis have a lot of characteristics that are similar and some that are not. The Indian Ocean Tsunami and earthquake occurred on Boxing Day 2004, and probably this was the wake-up call to the world about the risk of tsunamis. There was a huge earthquake, magnitude 9.3, which was the second largest that is on record, and it caused a massive tsunami that spread across the Indian Ocean. And then about 7 years later, 2 years ago, in the 11th of March, Japan was rocked by another mega earthquake. Now these earthquakes are very rare. There's previously only been 3 or 4 events in the last 100 years. So when one of them occur, it's a remarkable occurrence. And again, similar type of thing, magnitude 9 earthquake, and it caused widespread shaking and a massive tsunami. Now the earthquake here, it lasted for about 10 minutes, so huge amount of time that the earth was shaking. And then not a lot of damage was done because of the distance from the epicenter to the locations. But once the shaking stopped, the similarities between these two events diverged. In Indonesia, people were shocked and scared, and they didn't know what was happening. They'd never felt an earthquake this big before. They tried to go find where their loved ones were. People near the beach noticed some strange signs. The water suddenly withdrew, leaving hundreds and hundreds of meters of sand on the beach. And they saw lots of fish that had died, fish that were stranded, and they went down and, as you do, go pick up the fish and you can eat them that night. Whereas in Japan, students and the population, they knew that following large earthquakes can be tsunamis. They'd had education. They have a warning system that warned them that a tsunami might come. For instance, in the schools, older students came and took the young students to shelters like they've done in drills every year. So these two different actions were quite dissimilar. Now, once the shaking stopped, about 20 minutes later, this is what occurred to the two populations. On the left, we have a movie from Banda Aceh, from the city centre, about 2 kilometres from the coast. And on the right, we have the Japan tsunami film from a helicopter surging through the Sendai plains. Now you can see the utter devastation that these events are causing, picking up huge amounts of debris, destroying everything in its path. The wall of water on the left is about 5 to 10 metres high. So those little white strips, they're about 5 metres high agriculture sheds. So absolutely devastating. Now for context, they were about 20 to 30 metres high. Okay, that's the peak height that was recorded in both these events, which is actually higher than the GA building. So when you leave to go for lunch or a walk or after work, take a look back at the building and think about what that would be like with a surge of water coming down on you that high. Following the event, everything was wiped out. The only things that were remained were multi-storey reinforced concrete buildings like the mosque in Banda Aceh, or some office buildings in the background in Japan. Everything else that's not strong was totally wiped away. So we can look at the outcomes of these events and start asking some questions. So why were they so different? In Indonesia, about 180,000 people died in Indonesia alone, about another 60,000 in Thailand and India and Sri Lanka, and in Japan about 16,000. Now if we normalise that to how many people were actually in the inundation area, the fatality rate in Indonesia in most places was about 20 in 100, or about 1 in 5. In Japan, it was about 1 in 100. So quite strikingly different outcomes. So why was that? Well, it goes back to preparedness. It goes back to that first slide, the reaction after the earthquake. Japan knew what to do. They'd been trained. they had done drills, they knew the risk, and they evacuated when they could. Still, some people couldn't evacuate or made the decision not to, and unfortunately they died. In Indonesia, no one was aware of what was to come after the earthquake. And we can put this in context of a disaster cycle, where on the top half we have what we call risk management, which occurs before the event, and on the bottom half we have crisis management, which occurs after the event. So if we go back to the first step that needs to be taken, it's assessing the risks, knowing the risks that natural hazards pose to communities. And from that, if we know those risks, we can then do mitigation, prevention, be prepared, develop early warning systems, and some hazards we can do prediction. Then an event occurs and we respond, recover, and then reconstruct. And then we reassess the risks from the lessons that have learned from that event. Now, if we consider this in the context of Indonesia and the Japan tsunami, Japan had assessed its risks, Indonesia hadn't. So this goes back to the fundamental point of risk information. And this is where GA comes into this disaster risk cycle. We actually do work in the full part of the cycle in different parts, such as in NEO, they do some of the response, and same with an NGIG. But what I'm going to be talking today about is assessing risks, to start off that risk management cycle. Many of you may have seen this before, but this is the risk triangle. It's what we like to think of to keep how to talk about risk in context of a hazard, which is the natural event that occurs, and that could be the amount of water in a tsunami or the shaking from an earthquake. Then we integrate that with exposure, which is where people live, where assets of interest or things that are important to the community are. So those two parts have spatial components. We know where buildings are located, we know where the water's going to flow or the shaking's going to occur. And we can integrate that with vulnerability, which is how those assets or people will respond once they're exposed to the hazard. And combining this together gives us a picture of risk. Now, usually we can't actually reduce the hazard for these events, but we can reduce exposure and vulnerability to reduce our risk. And if we put this in context of the risk management cycle, so this is from the Australia and New Zealand standards, we can see that we establish the context, and these three middle bits, identifying risk, doing analysis and evaluation, is what forms a framework for risk assessment. And once we've done that, we can start treating risks and reducing the impact from future events. So the challenge for us as disaster scientists and in the risk field is actually providing information that can underpin that prevention, preparedness and mitigation. So we need to develop information that's fit for purpose, whether it's for a multilateral agency looking at prioritisation at a global level, or for national governments who might want to identify which regions need to be focused on. And then at a local level, again, a different bit of information is needed. We need to actually help disaster managers and local community prepare for when an event will strike to them. And that usually involves doing scenarios and helping them plan for evacuation or response. Now, these projects that I'm going to be talking about have been funded by AusAid. And a lot of people often ask us, why is AusAid interested in this work? So I think it's important to reflect on some numbers and some, I guess, the experience with disasters and international development. In the past 20 years alone, disasters have affected nearly 4.5 billion people, which is nearly the population of the globe. And about 1.3 million have been killed. So a huge amount of people. And in terms of economic losses, there's been about $2 trillion. So we're talking huge amounts of money that are being wasted on recovering and responding to natural disasters. Now, importantly for AusAid, 95% of these fatalities have actually occurred in developing countries, and 85% of the people affected, so that 4.4 billion, were from the Asia-Pacific region, so our neighbours. So they're the people that have been affected by these disasters. And surprisingly, the economic losses from disasters have actually outstripped international aid in those developing countries. So you can really see that the impact from disasters is eroding the gains made by international development. So it's in AusAid's interest to actually try to reduce the impact from future disasters so that they make sure it's not impacting their main business, which is international development and poverty reduction. So I'm going to talk today about 3 case studies. at 3 different scales. So talking about different products that we've developed and showing how they've been assisting in disaster risk reduction activities. So the first one I'm going to be talking about is at a global scale, which is a project that we did with the United Nations, developing a report for global assessment of risk. The second project is the Indonesia Tsunami project, which Chris mentioned. And so this is developing a national snapshot of tsunami hazard for Indonesia. And at a local setting for the island of Tonga in the Southwest Pacific, providing information that's helping local disaster managers plan for the next event that may occur. So before I go on to that, I just want to go over why tsunamis are so devastating. People have heard about tsunamis, people may know a little bit about the background, but they're very different to what we can think about when we usually go down to the south coast and go surfing or go for a swim. Now, 85% of tsunamis are caused by earthquakes, and usually in subduction zones where we have one plate subducting beneath the other. Now, over time, those plates become locked, and the overriding plate gets sucked down by the subducting plate, and this causes stress along the interface. Now, over time, that stress is then built up and releases suddenly in an earthquake. And then it causes a displacement of the water, which sends waves travelling in both directions. So if we look at that again, so we have the plate subducting, and then the stress is building up here, and you can see it getting dragged down and then pushed up here. Now, when an earthquake is released, a large earthquake, it displaces the sea floor and then displaces the surface of the water, which creates a ripple, which then propagates across the ocean. So this is much like in a bathtub where you're having a bath and you push up the water from below, and it creates a ripple across the bath. Now, in the deep ocean, the tsunamis can travel at about the speed of a jet plane, 700 to 900 kilometres per hour. Now, they're only about half a metre to a metre in height, and so they're barely noticeable in the deep ocean. Now, the other difference is that they've actually got huge wavelengths, so it can be hundreds of kilometres between the distance between 2 peaks of a tsunami wave. Now, as that wave approaches the continental shelf, the front of the wave slows down, much like a breaking wave at the beach. And this causes all the rest of the water behind it to start stacking up, causing the wave to increase. So as you can see, the distance decreases from hundreds of kilometres to tens of kilometres by the time it reaches the continental shelf. Now, that process continues as it reaches the beach, and usually we see a withdrawal at locations near the source of the earthquake. And then the tsunami is manifest by this, basically a surge that comes right up the beach. So it's not like a typical ocean wave, which has about a cycle of about 5 to 10 seconds, so it comes and then it goes. This thing can last 20 to 30 minutes surging in, like you saw on the video in the Sendai Plains or in Banda Aceh. Then after 20 minutes it withdraws and then leaves the seabed showing, and then another wave will come. Now, typically for places like Indonesia, Papua New Guinea, Philippines that are close to the earthquake source, there'll be about 3 or 4 waves that will cause most of the devastation. Now, the first wave is not necessarily the worst. So sometimes you can see a wave come in and then it won't do much damage and it will withdraw, and then a larger wave will come in and do most of the damage. So tsunamis, as I mentioned, occur mostly in subduction zones. So if we look at where tsunamis have occurred in the past 1,000 years, we can see that they are predominantly confined to the Pacific Ring of Fire. So the major subduction zones around the Pacific Ocean, the Indian Ocean, and then a few in some of the large faults in the European. Now, most of these are what we call local or regional tsunamis. So they do most of the damage locally or in islands nearby. And some of them, the very large ones, are distant tsunamis, so they'll cause a lot of damage locally, but can also propagate right across the ocean basin and cause damage on the other side of the ocean, particularly these Chile events and some of the Japan and Alaskan events. So as we saw in the video, a tsunami is a wall of water. They're impossible to outrun. They're travelling at about 10, 20 metres per second once they come on land, so you're not going to be able to outrun it. if you get caught in it, there's so much debris that generally you're not going to be able to stay afloat, and that usually causes most of the difficulties for people. Now, generally a person can stand up in about half a metre to 0.7 of a metre of flow depth for a tsunami. If it's above that, they'll get swept away. So you don't need a big tsunami to cause a lot of damage. Now the debris, it just picks up anything that can be floated, usually wood or cars, boats, tanks, and then it just carries that. So that also causes further damage because that will then collide with other structures, causing more damage. They can actually scour and float buildings as well. This is an example in Japan where this building here, the foundations have been scoured out by the tsunami, much like happens if you put your feet in the water at the beach, and the building then was floated and tipped on its side. So even large buildings can be affected by this process. And then finally, fire can happen. So once petrol tanks picked up, boats, or there's gas tanks, they can often catch fire, and the wood debris then catches fire as well, and they can cause large floating flotillas of fire. Now if we look at how often tsunamis occur, we can see that these are fatal tsunamis from 1900 to present. We can see that there's actually been a quite regular periodicity of tsunami events. Now most people only heard about tsunamis post-2004. That was the big wake-up call, and that was this large event here that killed over 100,000 people. But previously there had been events, but people hadn't really been taking notice of them. There have been a few people that have been researching them, Phil Cummins and GA for one, but most of the attention has been after here. But you can see that there has been a consistent record. So if we think that the last 100 years is anything to go by, then we will expect about an event that would cause 10 to 100 fatalities about once every year. And that has basically happened for the last 10 years as well. We would expect an event that would cause 100 to 1,000 fatalities about once every 4 years. 1,000 to 10,000 every 6 years, and these catastrophic events that cause greater than 10,000 fatalities about once every 90 years. So we've had 2 of those in the last 100 years, but before that there was about an 80-year period that there wasn't one. So we can see that there are frequent tsunamis that do cause fatalities, but these ones are the ones we need to worry about, these very large events that occur infrequently but can cause devastating impacts. And this is highlighted by, if we look at the number of fatalities by tsunami, we can see that about 85% of the fatalities are from just 6 events out of about 200 that have occurred. Now, this is the Indian Ocean and some other ones, including Japan. So we can see that most of the impacts are caused by very few events with low probability. Now this poses a challenge for disaster managers, because if we look at some other hazards, compare their frequency and impact, we have the typical annual events, which like flood, bushfire, tropical cyclone, they occur regularly and their impacts are generally small compared to some of the more catastrophic large events like volcanic eruptions, earthquakes and tsunamis. So if you're a disaster manager, these are the things that are occurring year to year that you're going to be prioritising to plan for. But these ones are the ones you've got to watch out for, because they're the ones that can sneak up and cause huge impacts, cause tens of thousands of fatalities and billions of dollars of economic losses. So this is one of the challenges in the tsunami space, is actually keeping the interest in these events when events have not happened in recent years. And it's interestingly, the funding cycle of tsunamis actually goes up with the number of events that occur. So how can we mitigate against tsunamis? Well, tsunami warning systems are the most effective way. Although they're fairly costly, they provide that warning, that 10-15 minutes that is needed for people to evacuate. The cheapest way, and also a very effective way, is evacuation planning. So knowing where the tsunami will flood if it does occur, and for people doing drills and knowing the early warning signs, the natural early warning signs that they can look out for when a tsunami may occur following an earthquake. And in some cases in Japan, they've used coastal protection and land use planning, such as tsunami walls here, but they actually prove very ineffective in the Japan tsunami, so they're only really suitable for small events. But most of them in Japan were actually picked up and carried as debris and destroyed a lot of buildings because of that. So if we go back to the projects, again I'm going to talk about at the global, national and local scale. So tsunami hazard assessments that we're doing, we can do them in different ways. We can do it using historical accounts. We can look back at descriptive records from history, but these only go back about 100 to 500 years, and they're often dependent on record quality. We can use geologic deposits. These go back thousands of years, so long-term picture, and we can use them to create where tsunamis flooded in the past. But it's often usually dependent on preservation. In tropical areas they're not preserved as well, and they only usually record the very large events. And what we choose to do at GA is use computer simulations. Now this allows us to simulate any hypothetical event. So we can do a lot of what-if scenarios. We can also recreate historical events if we like. And we can do this to simulate tsunami in the oceans and on land, depending on the purpose. And we take a two-model approach at GA, so this is for domestic and also the international work, where if we're doing a regional or national hazard assessment or risk assessment, we use an approach where we solve the linear shallow water long wave equation which propagates tsunamis through the deep water. Now this is actually computationally fast because it's solving linear equations, and it allows us to model hundreds of thousands of different events and create probabilistic forecasts at the coast. And it can be used as a prioritization tool. Now on the other hand, when we're wanting to look at community impacts, we use detailed inundation models, such as the Anuga model developed here at GA. So this uses the nonlinear wave equation, which is required because we're in very shallow water depths and we're modeling the wetting and drying. And it's because of that it's computationally expensive. So we can only model about 10 to now maybe hundreds because of using the NCI scenarios. And this is particularly useful for evacuation and land use planning. So when we're doing regional assessments, we're trying to answer questions like, what's the area most likely to experiencing a damaged tsunami to help prioritisation? Or what's the chance of a tsunami occurring in a community? That's from a disaster manager's point of view. And that can be used to help planning. And then what is the height if a tsunami occurs that we would expect over 100, 500 or even 10,000 year return period? And that again can be used for planning. And we answer these questions in a probabilistic framework, which is called a probabilistic tsunami hazard assessment. And this allows us to calculate probabilities of exceeding a certain tsunami height. Now this is much like a weather forecast that you see every day. You may not know that this is a probabilistic forecast in the weather, but they're giving you a hazard level range, which is 2 to 5 millimetres, and then they're giving you a chance or a probability of that hazard level being reached. Now when we do tsunami hazard assessments in a probabilistic method, we actually use a similar approach where we have a probability and a hazard level. And the way that we do this is we first define earthquake sources. So in this case we have the Sundarak subduction zone here, and we discretize this up into small, what we call subfaults, so small little subfaults. And then for each of those faults we create a synthetic earthquake catalogue. And earthquakes generally follow something called a power law, which means that if we plot the number of earthquakes that exceed a given magnitude on a log-log scale, it's linear. And we can actually use the slip rate or plate convergence to try to derive one of these curves which tells us how many earthquakes we'd expect on that subduction zone. And then from that we can then model the tsunamis caused from those earthquakes. And then for each of those little subfaults that I showed, we do a computer simulation modelling the tsunami from the source across the ocean. And the main input for this is a bathymetry model, which we can use some of the global models for deep water or multi-beam bathymetry derived from GA or other people for the local areas, where the bathymetry is represented by a grid, and we track the tsunami across each of these cells. So we record the velocity and amplitude across the cells over time. And from that, we can then come up with an estimate of the wave height, the maximum wave height from one of those little subfaults. Now, each of these little subfaults is what we call a tsunami Green's function. So this means that we model a whole lot of each of these subfaults with 1 metre of slip, and this is called a unit source. And what this allows us to do is that because we're solving the linear wave equation, we can actually sum together lots of little subfaults to actually make a larger event. So this is a unit source with 1 metre of slip, and if we want to make a bigger event, we can simply add up all the tsunamis from multiple subfaults, in this case 4 by 3, and then we can multiply the wave height by the amount of slip that occurred relative to the 1 metre. So this allows us to do an efficient way to calculate hundreds and thousands of different tsunamis. And we store all these tsunami greens functions in a database, which means it can be used later. Now, the benefit of this computationally is that it takes about 4 hours to run a single simulation for one subfault. And so when we're combining those, it takes only about a minute. So you can see the time savings by adding up and using this tsunami greens function approach. So, for example, if we were modelling 100,000 events, it would take us about 62 years on a single processor if we were modelling all of those events using full simulation. Whereas with the greens functions approach, we only model about 4,000 or so, which is the number of subfaults, and then the rest of the events we add and scale, and this means it only takes a few months. So this is the way that we can model so many events. And the other benefits is that it can be used later for hazard assessments. People can use that database of tsunami greens functions, and it can be used in a warning system. And that's actually what's been used for the Australia tsunami warning system with GA and the Bureau. Now, once we've modelled all of our events, we have locations around the coast where we want to calculate the hazard. And these are our hazard points. Typically for, say, Indonesia, 5 to 10 kilometres. And what we do is we take all the events that have been recorded at one hazard site, and we have the probability of those events from that earthquake relation I showed you. And from that we can derive a hazard curve. Now a hazard curve tells us that the probability of exceeding a given tsunami amplitude. And this is the annual probability. And we can also express this as the return period, which is the inverse of the annual probability. So an annual probability of 0.1 is a return period of 10 years. So that means we would expect, on average, that wave height to be exceeded every 10 years. So to look at, say, a 500-year return period and what the hazard would be, is we simply go from the 500-year return period until it intersects the curve, go down to the hazard line here, the amplitude, and that gives us about 2.6 metres. Now we can do that for each of the hazard curves for all of our sites to create a hazard map, and in this case a 500-year return period map. So you can see all the dots, and these are the hazard values for a 500-year return period. Now we can take this one step further. At the moment it's only at the coast or the near shore, but there's actually some methods that we can use to take that into run-up. So this actually tells us information of where the tsunami is going to strike on land. And this is important for national or regional assessments because it's too computationally intensive to model that with full simulation onshore. So we can use this proxy approach where we can use amplification factors to take our probabilistic heights at the coast or just offshore and estimate where that will go on land. Now the other part of a probabilistic methodology is that we include uncertainty. So this is the fundamental part, is that we're uncertain about a lot of parameters and we want to include those in our models, so that's expressed in our results. And with the NCI, a lot of other areas of GA can now start looking at including uncertainty in their modelling as well. And there's two types of uncertainties. The first type is what we call epistemic uncertainty. And this arises from a lack of knowledge about a process. And this can be reduced with more information. So if we collect more data, we wait for more events to occur, we can actually reduce this uncertainty. And this could include something like the slip rate on a fault or the plate convergence. If we have better data, we can actually reduce the uncertainty. Or it could be how an earthquake ruptures. Does it rupture in segments, or does it rupture in a large, huge event? And we can include this uncertainty in a thing called a logic tree. So for a source zone like the Sunda Arc, we can have different branches. So it's like a decision tree where we can have segmentation or no segmentation. And then we can give that a weight that adds up to 1 for each of these decisions that are developed from, say, a consensus or a workshop. Then we could also look at the maximum magnitude on that fault. People may think that it an earthquake fault has different maximum magnitudes, so we can account for the uncertainty in that, and then also the slip rate. And the way that we use this logic tree is we sample this logic tree in every possible way to create lots and lots of different events. So we're including that uncertainty in our synthetic catalogue. Now the second type of uncertainty is aleatory uncertainty, and this occurs from natural randomness of a process, and this can't be reduced with more information. So this could be something like where the slip occurs on a fault, and that's usually random. But the way that we can include this is that we can model lots of different earthquakes with different slip patterns and then come up with an estimate of how the wave height will be distributed. And then for any given wave height, we can estimate the probability that that would be exceeded using a probability distribution function. Now on to the case studies. So the first case study I want to talk about is a project that AusAid funded us to do that started in 2012, and that was to work with the United Nations to develop a global assessment report on disaster risk reduction. So this is a biannual report, and it ranks countries by risk level for a range of natural hazards. Now GA was involved in the earthquake, tsunami and volcanic ash of this report. And I'm going to be talking about the tsunami part that we contributed to. And this is kind of like the IPCC for climate change, where it's providing a high-level overview of the snapshot of disaster risk. So for tsunami, we're looking at the hazard and exposure for a 500-year return period, which is getting into the worst-case area. And GA contributed data for Southeast Asia and the Southwest Pacific. So we included only the major tsunami sources, so lots of the smaller faults we didn't include because we're looking at a global scale, such as the Tonga Kermadec and the New Britain Trench, and then the Sunda Arc and the Philippines subduction zone. And from that we developed a 500-year return period hazard from the probabilistic assessment, which gave us our wave heights at the coast. And then we tried to use that to integrate exposure and data of population and economic data. So we took our information at the coast, which was our tsunami heights, and from that we estimated the run-up for those events, so how high it would get above the elevation. Now, using a GIS approach, we then interpolated across the coast to come up with a maximum water level for this 500-year return period event. We then used a digital elevation model, in this case the shuttle radar topographic mission, because this is available globally. And then we subtracted the DEM from the maximum water level to get a potentially inundated area. But we wanted to limit how far the water would go and land in very flat coastal plains, so we had an attenuation law where the tsunami would attenuate and dissipate out over some distance from the coast. Now this gave us an inundation area. So this is applied on a global scale, remember, so it's quite a coarse approach, but we needed to do that for a global assessment. We then took two different types of exposure data: population data from Landscan, which gives us the amount of people that live in a square kilometre across the globe, and the UN developed an exposure database of the amount of gross domestic product, or what we could call economic exposure, across the globe. Now from that we can then overlay that with our inundation area to come up with an exposed population or capital. And an example of this is shown here, which is the population density, with red being quite dense across 3 different areas. And in terms of the global hazard, we can see that red is high, is a lot along Indonesia, Japan, South America, and a little bit on the west coast of Australia, and some patchy parts in the Pacific Islands, depending on the orientation of the island. And from this, we can then rank countries by the amount of people exposed in absolute numbers and also relative numbers. And we can see that a lot of the countries in our area, in our region, Indonesia, the Philippines, Tuvalu, have actually got quite high population exposure to tsunamis. Now Japan's obviously the standout for both population and a relative sense and absolute sense. Now if we look at economic exposure, we can see that it's the top's dominated by a lot of the rich countries, but interestingly China's in there. And relatively, we see that some of the small island states like Maldives, Solomon Islands, New Caledonia, Seychelles have high relative economic exposure. And in particular, if we look at small island states, we see that many of the Southwest Pacific islands actually have a very high exposure to tsunamis, both for their economic capital, because lots of the cities and towns are built on the coast. And so this really highlights the picture, a snapshot of where tsunami risk is concentrated around the world. Now this information is being used at a high multilateral agency level to prioritise funding. It's also meant to highlight to disaster managers, to governments, to policymakers where tsunami risk but also other natural hazard risk is concentrated. And we can see this was picked up by the ABC where they wrote an article about the report that said that the Pacific countries are actually ranking top for disaster risk exposure, and that's on the relative sense. So hopefully information like this, it gets out and it generates interest and moving towards taking action on mitigating these risks. Now the second case study is the Indonesia Tsunami Project. Now in this assessment we wanted to develop a national picture of tsunami hazard across Indonesia to help national level disaster managers prioritise investment. And this was funded by AusAid through the Australia-Indonesia Facility for Disaster Reduction and involved collaboration with 7 Indonesian agencies, and it was actually led by GA because we were taking the methodology that had been developed in Australia and applying it to Indonesia. Now, pre-2004, tsunami science in Indonesia was pretty sparse. There'd been a bit of work looking at coral uplift in the Mentawai Islands, but not much had been done on then looking at the impact of that and how that would cause tsunamis. Now post-2004, it was flooded by donors. We had the Dutch, the Germans created a tsunami warning system, the Japanese, Singapore, and the Chinese as well. So it became a very crowded space. But you can actually see that most of them are focusing on Sumatra and a little bit of Java. So eastern Indonesia was totally neglected. So there was actually not a national picture of tsunami hazard or risk across Indonesia. And so we formed a collaborative project with everyone that was doing tsunami science in Indonesia, which is these 6 agencies. Everyone that does something with science or water likes to do tsunami. So we worked with the Geologic Agency, the Geophysics Agency, some universities, the CSIRO equivalent, and the Ministry of Fisheries was involved as well. Now if we look at fatal tsunamis in Indonesia, we can see that they've actually occurred more frequently in eastern Indonesia. And so this highlights the need to actually develop this national picture of tsunami hazard to help prioritise where investment and mitigation activities need to occur. So we used an earthquake source model that was far more detailed than the global approach. There was about 31 sources. 2/3 of them were local faults and subduction zones around Indonesia, but also some from the northwestern Pacific that may impact Indonesia. And we used the earthquake recurrence information from a recent seismic hazard map for Indonesia. And we generated about 110,000 synthetic tsunamis. So from this we developed a range of products, maps that show for each sub-district the relative or the tsunami hazard for that district, and then you can compare that nationally. So this is for a 100-year return period, and we can see that the hazard is concentrated highest along the Sunda Arc, but also interestingly in North Papua and North Sulawesi. If we go out to 500 years, we can see now that eastern Indonesia has quite high hazard in most parts, but the hazard's mostly dominated along the Sunda Arc, where we're getting wave heights of 10 to 20 metres or even above 20 metres for the Mentawai Islands offshore Sumatra. And if we go out to what we call the worst case hazard, the 2,500 year return period, we can see that the hazard's mainly dominated along Java Sumatra, but pockets of high hazard in eastern Indonesia. Now the reason for this is that the largest magnitude of earthquake can occur along here is larger than can occur on these smaller faults. So that's why the hazard is higher. But if we put the hazard in a different context, which is actually a probability of exceeding a certain level, we can see that there's these big hotspots in eastern Indonesia. So this map is showing us the probability or annual probability of having a tsunami warning which is linked to a tsunami of about 0.5 metre at the coast. And we can see these red areas have a chance of 1 in 10 every year of experiencing a tsunami greater than 0.5 metres. So this would cause a little bit of marine damage and maybe cause some problems for people on the beach. Now, for an event greater than 3 metres, and this is what the Indonesian tsunami warning system would call a major warning, we can see that the probability is about 1 in 50 to 1 in 100 each year of experiencing this warning. Now this is a little bit lower in eastern Indonesia where it's about 1 in 500 to 1 in 100. So a 3 metre tsunami would definitely cause fatalities and damage. So this information can be used to help prioritise where tsunami mitigation should occur. And again, we can do this for the coastal cities. These are the provincial capitals, and we can see that Denpasar and Bengkulu have the highest hazard of experiencing a 3 metre tsunami, the highest probability. And for small towns as well. So again, this is a tool that's been used by national level disaster managers to help them prioritise where to invest. So we found that there's about a 10% probability for parts of Bali, Lombok, Sumatra, Java and North Papua of having these major tsunamis. For a smaller tsunami, there's a smaller chance for Sulawesi, which is here, Seram, and for Flores along here. Now in terms of the hazard level, this is dominated along the Sunda Arc, but interestingly there's a large hazard over 10 metres in eastern Indonesia. And we did a quick calculation of the number of people that live within about 5 kilometres of the coast in the high hazard areas, and it's about 27 million people. So these people who may live in the inundation zone or may travel there for work every day, greater than the population of Australia. So it really highlights the problem that tsunamis pose in Indonesia. Now, we finished this work, and then there was luckily an event that occurred that didn't cause any fatalities. It was the large 8.6 earthquake that occurred in the intraplate region offshore Sumatra. Now this generated a tsunami warning with widespread panic. Now everybody did not follow any of the information that they'd been taught in education. They all jumped in their cars and their motorbikes, and it ended in traffic jams. Nobody evacuated in time. Now, this really bothered the president, SBY, and he came up with a presidential decree. And in Indonesia, the president can come up with a law, and he can say, I want the government to work towards this focused goal. And he called this the Tsunami Master Plan. And he wanted to invest a lot of money in preparing communities better and giving them options of evacuating in the high-risk areas. So our collaboration project provided the information to the National Disaster Management Agency, which then used that as a prioritisation tool for investing over $300 million in building vertical evacuation structures. So these maps are being used to then roll out building of large-scale vertical evacuation structures. Now there's 20 being built this year, and that's going to increase to 40 next year, and with about 100 being built over the lifetime of the project. So this information is underpinning quite significant investments. Now the third case study is the local scale, and this is at Tonga. Now Tonga, located in a remote part of the southwest Pacific, and the capital, Nuku'alofa, has about 25% of the population. Now it sits on a peninsula, which isn't really good for evacuating from tsunamis. Now they haven't experienced a large tsunami before, but the concern is that the Tonga subduction zone is actually the fastest subduction zone in the world. So it's accumulating a lot of strain, and we don't know if that's going to be released in an earthquake or it's being released silently. So there's a lot of unknown there. But the key is preparation. So AusAid funded a public sector linkage project that was led by Phil Cummins and worked by Lauren Power as well, that looked at developing inundation scenarios and evacuation analysis to help underpin planning. So in this case, we wanted to develop detailed inundation models to look at where the flooding extent would occur on the peninsula. And this was used for the evacuation mapping, and then contingency planning, which is what you do after an event. Now we use the Anuga model, which is developed at GA by Ole Nielsen and the domestic program, and it's also developed out of the ANU as well. It's a free open source software, and it can model shallow water flows across land. And so in this model, we represent elevation data by a triangular mesh shown here. So this is, say, a channel on land, and we can have different resolutions of mesh. So in deep water, we can have coarse resolution, and as we get closer to the coast, where we're more interested, our mesh gets a lot finer till we get to the point where a triangle is about 20 meters in size, in real size. And then we apply a vertical deformation where our earthquake occurs, and we propagate the tsunami across the ocean and onto land to give us a picture of inundation. Now, the reason we use the Anuga model is because it solves the nonlinear shallow water wave equation, which is important for the wetting and drying process that occurs on land. So Phil modelled a magnitude 9 event, which was essentially a replica of the Tohoku event, and put that on the Tonga subduction zone. Now, the bad news is that it inundates pretty much the whole of the peninsula, most of the city, with a couple of pockets here where there's hills, but most of the main business district and the King's House is located on this peninsula. So we wanted to test a new methodology to try to help decision making around evacuation modelling. So we used a method called a cost distance approach to look at how people could evacuate on foot, which is the method that's preferred when evacuating. And this looks at the distance and the time that it takes to evacuate and considers two parameters, slope and land cover, because those are going to affect the time that it takes to walk anywhere. So the way that we do this is we break up our area into a raster, and we can do this analysis in a GIS package like ArcGIS, and we assign costs for our two characteristics. So if the slope is steep, it has a high cost because it takes longer, it's harder to walk and it's slower to walk up a slope. And for land cover, a rougher surface has a higher cost. So road is the lowest cost, and something like bushland is the highest cost. And then we calculate the accumulated cost for our raster, and the best evacuation route is the path of least cost. So that would be something like this. And then we can work out the time that it would take for someone to go from a safe spot, which is the wet cell, the hazard cell, to a safe spot, which is the dry cell. Now, the data for the area, we did some GIS analysis and developed a slope map, and then assigned a percentage of a normal walking speed that someone could walk. So if it's flat, they can walk at 100% of the speed, and if it's 5 to 10%, about 60% of the speed. And this is based on testing by published literature. Then we derived land use type from satellite imagery and have roads and buildings and vegetation and sand and grass. And then assigned the percentage that someone can walk of their speed for these different land use types. And then from that we can derive a speed map. And this shows how fast someone could walk across any part of the map. So you can see the red lines are the fastest, that's the roads, and then the next is these kind of open lands here, and the blue is buildings or water, which you can't walk through. So then we look at our flooded area from our tsunami again, and we use the evacuation modelling to calculate the evacuation time in minutes from any point to our safe areas. So our safe areas are here. Now you can see that at the end of the peninsula it's going to take over 30 minutes for them to evacuate to this nearest hill. So these areas are actually unsafe because the tsunami is going to arrive in 25 minutes. So we can use this to then combine it with population data to estimate the amount of people that would be left in that unsafe zone. So you can see that about 700 people would be in that area that wouldn't be able to evacuate in time, out of about 17,000. Now, if people wait after the shaking stops and delay their evacuation, the situation becomes worse, and now about 1,500 people would be in the area that would not be able to evacuate. If they wait 15 minutes, 10 minutes for the large shaking, 5 minutes to look for loved ones, it's even worse, about 3,000 people. So now we're looking at nearly about a quarter of the population in the area would potentially die because they would not be able to evacuate in time. So this helps disaster managers know how important it is to do that initial reaction and evacuate quickly. Now we can also do what if situations. So if we put a vertical evacuation structure here, you can see now that the evacuation time is suddenly reduced for this part of the peninsula. And only 11 people, which is within the margin of error, would actually be left in an area that couldn't evacuate. So this kind of tool can be used to help decision making. This information was presented at a workshop which was developing evacuation planning, and the main thing it did is it generated discussion about what people might be experiencing if an event occurred, what are the timeframes required. And in the future we hope it could be used for developing mitigation scenarios, so helping do a most cost-effective approach by siting vertical evacuation buildings or towers. So finally, I'd like to just emphasise that we've seen tsunamis can cause devastating impacts. Tsunamis are not a new phenomena, they're going to continue to occur, and with population increasing, the impact is going to become worse. But we know that mitigation and preparedness works, as was seen in Japan, compared with Indonesia in 2004. But the decisions on mitigation have to be underpinned by fundamental and accurate science and hazard and risk information. And it has to be targeted to the use, whether it's at a global level, regional level, or at a local level. And at GA, through our projects with AusAid, we've developed a range of these products that are being used now across the globe in Indonesia and Tonga to help reduce the impact from future events. Finally, I'd just like to say that this work is obviously not just my own. It was done in collaboration with colleagues from Norway for the UN report, Indonesians, and GA people Lauren, Phil, and also John O'Griffin as well. So I'd like to thank you very much.